let's take a brief look at one of two predominant theories of bonding between atoms. The one we will take a brief look at is called Valence Bond Theory, and the other theory is called molecular orbital theory. Both have their advantages and their uses. So what valence bond theory says is that bonds between atoms are constructed by overlapping the orbitals of those atoms that have unpaired electrons. And when they have unpaired electrons, they're able to form a bonding pair of electrons in an atomic orbital. Each atom will contribute an atomic orbital and an unpaired electron to form the bond. So for instance, if I took two hydrogen atoms, each hydrogen atom has an electron configuration of 1s1, 1s. So there's one unpaired electron in the valence orbital of each of those hydrogens, and what they'll do is they'll share those electrons, pairing them up, one spin down, to form a bond. So I would call the orbital overlap for dihydrogen, since their valence shells are 1s and 1s, this would be a 1s, 1s orbital overlap, or the orbital overlap of two s orbitals. Let's take a look at HCl. For HCl, we've got 1s for hydrogen, and we've got, if we look at the periodic table, says that chlorine's unpaired electron in its valence shell is in a 3p shell. So we can look at chlorine as having 3p5, that's how many electrons are in that 3p subshell, and it will contribute that unpaired electron in the 3p, and what we'll have is the orbital overlap of an s and a p orbital. If we looked at two chlorines in diatomic chlorine, each one has that 3p5 electron configuration in the valence shell for chlorine. They're going to overlap the unpaired electrons in the 3p orbitals, and so what we would have here is the overlap of 2p orbitals. Very specifically, we would say that is a 3p orbital overlap. Over here, we would say this is a 1s orbital overlap. Here we would say this is a 1s 3p orbital overlap. Taking it just a little bit further, what would be the orbital overlap for, let's say, HBr? So if I had HBr and I wanted to know the orbital overlap, I would just look at the electron configuration in the valence shell for hydrogen, 1s1, and then over here for bromine, bromine has an orbital overlap that's in the 4p. How do you know that? You go down here, you look, you find bromine, and it's in the 4p subshell where we find the unpaired electron, because bromine's electron configuration in the 4p subshell is 4p5. That's how we know there's an unpaired electron there. And so the orbital overlap for HBr would be 1s 4p. For Br2, since we're in the 4p subshell, the orbital overlap for Br2 would be between these two unpaired electrons. These are atomic orbitals. That's what valence bond theory, that is the basis for the formation of a covalent bond in valence bond theory, and they would share that orbital in the 4p subshell and form a bond by pairing up those electrons. That's valence bond theory. It's just the overlap of unpaired electrons in atomic orbitals. Now, problems arise with valence bond theory when we look at molecules such as methane, CH4. And if we study methane, we know that methane actually has a tetrahedral electron pair geometry and molecular geometry, but it's the tetrahedral electron pair geometry we're going to focus on, because that is what creates those 109.5 degree bond angles. So let's look at what valence bond theory would say about carbon bonding to four hydrogens. So if I look at the valence shell electron configuration for carbon, I've got 2s2 and 2p2. Now there's only two unpaired electrons in the electron configuration for carbon, which means that according to valence bond theory, it should only be able to make two bonds. but we know that it can make 4 bonds and that they're absolutely equal at 109.5 degrees when carbon makes 4 bonds. So the first step in hybridization is to promote a lower energy electron to a higher energy state. So what we'll do is we'll take one of those 2s electrons that were sitting down here at a lower energy state, and we'll promote them up to the higher energy state of one of the 2p orbitals. One of the 2p orbitals was empty for carbon. Now we've got, by paying an energy price, we were able to promote one electron to a higher energy state. What we know about the p orbitals are that they are all at 90-degree angles to each other, px, py, pz, in a three-dimensional coordinate system. And if that were the case, even though we can now make 4 bonds after promoting a lower energy electron to a higher energy state, what that gives us is 3 bonding pairs of electrons, 3 orbitals at 90 degrees, and then 1 hydrogen atom that's bonded at some unknown angle because of the s orbital. So the second step is to equalize the 2p and the 2s orbitals to get these orbitals at the same energy level. So we pay an energy price and we move the s orbital up to a higher energy state, and we lower the energy state of the p orbitals. Now all orbitals are equal in energy, and the third step is to combine the 1s orbital and the 3p orbitals. These are all p orbitals. There are 3 of them. What we're going to do is we're going to combine them into 4 equal sp3 hybridized orbitals. Now all the orbitals are identical to each other, and you can think of it this way. It's as though we took 1s orbital and 3p orbitals, threw them into a blender, blended them together, and we came out with 4 sp3 hybridized orbitals. Now, all of that sounded fairly complicated. The practice of determining hybridization is actually very, very simple. Notice that we needed 4 orbitals that were absolutely equivalent to each other. Notice that we combined 1s and 3p's. Well, 1s and 3p's makes 4 orbitals. So the hybridization is going to be determined by the electron pair geometry. So if you have a tetrahedral electron pair geometry, molecular geometry does not determine hybridization, it's electron pair geometry. The hybridization will be sp3. That's because we needed 4 equivalent orbitals, combination of 1s and 3p's. That's the hybridization. So now what we're going to do is we're going to take a shot at figuring out the hybridization based on the electron pair geometry, how many equivalent orbitals are necessary. So if I have, and it's all based on electron pair geometry. So if I have 2 things around the central atom, you know that the geometry is going to be linear. The electron pair geometry is linear. If the electron pair geometry is linear, I need orbitals, 2 equivalent orbitals to handle the 2 things around the central atom. Every hybridization scheme starts with s because that's the lower energy orbital, and then they go to p. Since I'm going to need 2 orbitals, that's going to be an sp hybridization. sp is linear electron pair geometry. What if I have trigonal planar electron pair geometry? I need 3 equivalent orbitals. That's going to be sp2. 1s and 2p orbitals combined form 3 sp2 hybridized orbitals if the electron pair geometry is trigonal planar. What if I need 4 things, as I did with methane, around the central atom? That means I'm going to have 1s and 3p's, or 4 sp3 hybridized orbitals. So the hybridization there would be sp3. If I have trigonal bipyramidal, I have 5 things around the central atom, and that means that I'm going to have to pull in a d orbital in order to accommodate the extra orbital. So my hybridization would start with s. I would run through all the p's, so that's sp3. I include one more d orbital, so if my electron pair geometry is trigonal bipyramidal, my hybridization is sp3d. And for 6 things, which is the last you'll have to deal with, if I need 6 equivalent orbitals, octahedral is my electron pair geometry, I bet you can guess that my hybridization will be sp3d2. That's a total of 6. 1 s, 3 p's, and 2 d's all add up to 6 things around the central atom. So once again, linear, the hybridization will be sp. Trigonal planar, the hybridization requires 3 equivalent orbitals, sp2. Tetrahedral electron pair geometry, 4 equivalent orbitals, the hybridization will be sp3. 5 equivalent orbitals, trigonal bipyramidal electron pair geometry, sp3d. And octahedral, 6 equivalent orbitals. I need 1 s, 3 p's, and 2 d's. That all adds up to 6. That's octahedral electron pair geometry, sp3d2. A little bit of practice and you'll have it. For each of the following compounds indicate the hybridization on the central atom. And we are only talking about the central atom. We're looking for the electron pair geometry. If I draw the Lewis structure for water, I come up with an electron domain or electron pair geometry that is tetrahedral. That means I need 4 things around the central atom or 4 equivalent orbitals. I bet you know the answer. Here's CO2. If you remember, CO2 has a linear electron pair geometry, and so I need 2 things around the central atom, so I only need 2 equivalent orbitals. So what would the hybridization be there? CH4, we already know. We need 4 things around the central atom. You should be good at that one. SO3, well, we haven't drawn that one yet. But if we did draw that one, we'd find that it's trigonal planar electron pair geometry. That means 3 equivalent orbitals, and you can tell me the hybridization from that. SF4, well, I guess we're going to give you the answer to a clicker question. If you've watched the video, that should help you get a point on the next exam this week. And that's 5 things around the central atom. That means that the electron pair geometry of sulfur tetrafluoride is trigonal bipyramidal. I need 5 equivalent orbitals. So let's go back up to water. That's going to be sp3 because I need 4 equivalent orbitals. 1s, 3p. All adds up to 4. For 2 equivalent orbitals, I just need sp. And for 4 equivalent orbitals, I need sp3. Once again, I have tetrahedral electron pair geometry. For SO3, trigonal planar electron pair, I just need 3 equivalent orbitals, sp2. And sp3d because I need 1, 2, 3, 4, and one more 5 equivalent orbitals, sp3d hybridized for trigonal bipyramidal electron pair geometry. Sigma bonds are bonds that are along the internuclear axis. So if I were to take 2 1s orbitals and form a bond between the 2 1s orbitals in hydrogen, that would be a sigma bond. It's a little bit easier in practice to make that determination. I'll show you how. In a sigma bond, the electron density is along the internuclear axis. So here's our 2 hydrogens with 1s orbital overlap. You have 2 overlapping s orbitals, and that forms a sigma bond. If you can draw a straight line in the bond between the 2 nuclei, we call that a sigma bond. The other way to remember it is that a sigma bond is a single bond. This is also a sigma bond and also a single bond between the 1s and a p orbital because it's along the internuclear axis. There's a direct line of sight between the 2 nuclei, but this is overlapping an s and a p orbital to form a sigma bond. And here we have 2 p orbitals also forming a sigma bond because the 2 nuclei are lined up with each other. That's 2 p orbitals overlapping. This is a sigma bond. And once again, the feature of a sigma bond is in between the 2 nuclei. It is directly lined up between the two nuclei, and that determines that it is a sigma bond. The easy way to remember it is a single bond is a sigma bond. Let's look at sigma and pi orbitals. A single bond is composed of one sigma bond. A double bond is composed of one sigma and one pi bond. That's why a double bond isn't twice as strong as a single bond, because a pi bond isn't along the internuclear axis, it's above and below the internuclear axis. A triple bond is composed of one sigma and two pi bonds. So let's take a look at pi bonds. They're above and below the internuclear axis. That's where the electron density is. Pi bond above and below the internuclear axis between two p orbitals. The number of sigma bonds will equal the total number of bonds. 1, 2, 3, 4, 5 sigma bonds. Now we do notice that there's a double bond here, and if there's a double bond, that means there's also one pi bond. So in this molecule, which is called ethene, you have 5 sigma and 1 pi bond. Let's take a look at the central atom carbon with respect to the electron pair geometry around it. We've got 1, 2, 3 things around this carbon. If it's 3 things around the carbon, we know that the hybridization is sp2 because I need 3 equivalent orbitals for those bonding electrons. And so I have 1, 2, 3, that's sp2 hybridization. Same thing for this carbon. 3 things around the central atom, sp2 hybridization. And you can see that one sp2 hybridized orbital forms a sigma bond. You also have a p orbital that's forming the double bond. This is the pi bond above and below the internuclear axis, and then we have our sigma bonds between the 1s and the 2p hybridized orbitals that are coming off each of these carbons on the other side. Notice it is trigonal planar with regard to the shape of the molecule. 5 sigma bonds, 1 pi bond. This is another version of the sigma and pi bonding for ethyne, which is also known as acetylene. And we know this is a linear molecule. And if it's a linear molecule, it's going to be sp hybridized. That is, 1s and 1p orbital combined to form the sigma bond. And then we have the py and pz orbitals that are forming the pi bonds above and below the internuclear axis.